Well, good afternoon. So before we begin today, just a few things. First of all, homework set number 8 is shown here now. So these are for the whole week. Problems due a week from Wednesday. As usual, don't forget to bring your homework number 7 with you on Wednesday. That's when it's due. Also, just a note, I know that a student had a question about this last time, but just to make sure it's clear, the Clausius inequality that I derived for you specifically for the heat engine cycle, I said also applied to the refrigeration cycle. The equation delta Q over T for the cycle still is less than or equal to 0. The only difference is that with the refrigeration cycle, we're adding heat at low temperature and we're rejecting heat at high temperature. So, we have to have the QL over TL. That represents our heat input at low temperature. And then minus the heat rejection at high temperature minus QH over TH. So, just make sure that's clear in your own notes. Additionally, just a reminder, it says on the syllabus that your second midterm exam is coming up on Monday, a week from today, and it still is. The syllabus shows the sections that you'll be responsible for, so 4.3 through 7.1. Primarily, it's going to cover Chapter 5 material, but it could cover a little bit from the end of Chapter 4, particularly that deals with ideal gases and solids and liquids and the use of specific heats. If there's anything from Chapter 7, it'll just be basic concepts. I'm not going to have any of the problems like we started to, that we're starting to look at now. None of this is going to be on the test. So if anything, through the material on the Clausius inequality from last Friday, that's where the subject material ends for your midterm. Note here that you can use one note card. That'd be a 3x5 note card or equivalent. You can write on both sides if you choose to. And that's for, I'll let you use a note card also on the final exam, but you may want to put together a different note card for that. Nonetheless, this is a note card for this exam only. I'll let you know what will be allowed for the final exam. I will note that you're only allowed equations on there. You're not allowed to make drawings to yourself. You're not allowed to have, say worked out problems or step-by-step outline methods of solution or anything like that. It's just so that you don't have to memorize all those various equations. So you will be allowed one 3x5 note card written on both sides or equivalent. If you don't like using note cards and you just want to mark off the front and the back of a note card on a regular piece of 8.5 by 11 paper, that's okay with me. But everybody gets the same, 30 square inches? You can have a strip an inch wide, 30 inches long, for all I care. If that's how you like to get your information off of your note card, that's fine with me. So just want to make sure that it's all equivalent, front and back of a 3x5 card. All right, so let's just go back to where we were last time, please. Remember, we're in the middle of the derivation of what I call the increase in entropy principle. What I had done was I basically started by looking at two cycles, right? One was an ideal, the other was an unideal cycle, or if you will, one cycle had two processes that we call A and B that are both internally reversible. That is the ideal cycle. The other cycle that we look at is a little bit different. It uses the two processes we call A and C. Process C is an irreversible an irreversible process. So this is a different cycle than the other one, right? One cycle uses processes B and A, which is, reversible. The other processes uses C and A, and since part of that process is irreversible, then we would say that cycle is irreversible. And basically all I did last time was I wrote out the Clausius inequality for both the reversible as well as the irreversible cycle. And then I just related the two. I subtracted the latter from the former and ended up with this equation. Right, so again, this is really all just notes from last time. Where we ended last time was with this particular equation that I called equation A, and I'm just going to start up right again from there. Okay. Now let's note that process B is an internally reversible process, and hence by the definition of entropy, we can basically write that the entropy change, S2 minus S1, in fact, let me be a little more specific. We can write for process B that the entropy change, and remember, process B is one of these internally reversible processes, so as such, this is going to equal the entropy change along process B, or we can also say that it's equal to the integral of delta Q over T as we follow process B. Okay, so this is what we can write for process B, and we can do so specifically based upon our understanding of the definition of entropy, right? For an internally reversible process, which B is, the integral of delta Q over T is the entropy change. It is S2 minus S1. Okay. Now, what we also want to note, I'm just trying to leave this homework and other stuff up there if I can. Well, I guess there's no room for it. If anybody didn't get the homework assignment, just come up to the front afterwards or talk to one of your classmates. All right, so back to this. So what we also want to note is that entropy is a property. It doesn't matter whether we follow a internally reversible path, like path, or I should say process B, or we follow an irreversible path, such as process C. Entropy is still a property. It's going to apply to both processes as we go from point 1 to point 2. So, let's also note that the entropy change on process C will have to be the same as entropy change for process B. I mean, after all, B and C are both processes between the same 2 points, and entropy being a function that is a thermodynamic property or an exact mathematical function. It doesn't matter what process we take place, it's only dependent upon the state points. So both of these processes, B and C, go from 1 to 2, so their entropy change would have to be the same. Okay? So this would then equal, as it shows above, this will equal the integral 1 to 2 delta Q over T B. Okay. Now, this particular equation here, I'm going to call B, and then what I want to do is I simply want to plug B into the equation above that I called A. So let's just plug B into A, and in doing so, we would get the following. So let's see. The change in entropy using process C as we integrate from 1 to 2. Is going to have to equal, oops, let's make sure I get this right. Oh, I realize I forgot my integral signs up here. So if you just go back to equation B, the integral from 1 to 2 using process C for the change in entropy will equal the integral from 1 to 2 along process B for the change in entropy. So I'm sorry, I forgot those little integral signs in there. Nonetheless, if I plug B into A, then we would find that on the left-hand side of the equation, we just have this integral from 1 to 2 of dsc. And then on the right-hand side of the equation, we have our greater than side. This is going to equal the integral from 1 to 2 delta Q over T C. Okay. Now, why is this important? Frankly, I'm done with this derivation again, and just like the last derivation I went through, it wasn't exactly clear why I ended where I did. Let's make a note here. I selected path C, process C, in a completely arbitrary fashion, right? Process C is any irreversible process that takes place between 1 and 2, right? I could have picked process D, I could have picked process E, I could have picked process F, I could have picked any process, and I would find that the integral of the entropy change for that process is going to have to be greater than the integral of delta Q over T for that process. So essentially what I've just shown here, because of the way that I arbitrarily picked process C, is that for any irreversible process, this same equation, this integral of ds, has to be greater than the integral of delta Q over T. Okay. So let's see if I can write that out. But my choice of irreversible process C was arbitrary. I could choose any irreversible process, D, E, F, etc. I could choose any irreversible process, and the equation above is still valid. Okay. So therefore, what I can really say is that for any process, I'll just write it this way, the integral of ds is going to be greater than the integral of delta q over t. So in other words, therefore, this equation holds for any process. And maybe what I should really say is it's really only valid for any irreversible process, right? For an irreversible process, the entropy change has to be greater than the integral of delta q over t. So it's valid for any irreversible process. Now, with this in mind, maybe I could make some sort of a general statement. All right, so what would that general statement be? So in general, we can write the following, that the integral of ds has to be greater than or equal to the integral of delta q over t. Now, why can I make this statement, and why do I have an equal sign in there instead of a greater than or equal sign? Well, just keep in mind that when we defined entropy, entropy was defined as the integral of delta q over t for the internally reversible process, right? In other words, that's where the equal sign comes from. However, as was just shown in this previous derivation, the entropy change for an irreversible process, a real process if you will, has to be greater than the integral of delta q over t. So doesn't any process either have to be a real or an ideal process? In other words, doesn't it either have to be one that is irreversible or one that is reversible? In other words, doesn't the integral of ds have to be either greater than or equal to the integral of delta q over t? So that is this statement, okay? And let's keep in mind that, again, the greater than would imply that it's an irreversible process, or if you will, it's a real process. The equal would imply that it's an internally reversible process, or if you will, an ideal process. And it can't be anything else, right? If we go through a problem and mathematically we find that the entropy change when integrated over that process is less than the integral of delta q over t, well, I mean, that's just simply impossible. So we'll just note impossible. Now, perhaps one should also make the following statement, that if it's greater than or equal to, that satisfies the second law of thermodynamics. So satisfies second law. On the other hand, if we find that the entropy change is less than the integral delta q over t, well, clearly it violates the second law. So here we have another manifestation of the second law of thermodynamics, right? And this has absolutely nothing to do with cycles. Remember that the first time we looked at the second law was in the context of a heat engine cycle and a refrigeration cycle, and we found that one way to determine whether a cycle satisfies the second law is to show that its thermal efficiency can't be greater than the Carnot cycle thermal efficiency, or its coefficient of performance can't be greater than the Carnot cycle coefficient of performance, right? That was a statement of the second law. But that only dealt with cycles, and that was a problem for us, right? We now need to see if the second law holds for a process, just an individual process that goes from one state point to the next state point. And that's not a cycle, but as it's a process, we can use this particular relationship. Now, it's not clear how we use it yet, but just be aware of that. Before I leave this behind, let me also note that this could be written in different ways, right? We can just look at the differential portion of it. We can just say that ds has got to be greater than or equal to delta q over t. That's just another statement of the same thing. Or we can also write it simply that S2 minus S1 is going to be greater than or equal to the integral from 1 to 2 of delta Q over T. These are just different ways of making exactly the same statement. Okay. One other thing that this shows us, by the way, is that the entropy change for an irreversible process has to be greater than the entropy change for a reversible process, right? If this were a irreversible process, then the entropy change has to be greater than delta Q over T. If it's a reversible process, then the entropy change simply equals delta Q over T. So delta Q over T has to be greater for an irreversible process than it does for a reversible process. In other words, the entropy change has to be greater for a real and irreversible process. So, you're starting to understand now why we might call this the increase in entropy principle. Okay? The entropy change for a real process must be greater than the entropy change for an ideal process. All right. Well, now let's take it one step further. Let us now just consider the real process. So let's consider an irreversible process. Okay? And why don't we just say it's from 1 to 2. Now, we know what the entropy change is, at least based on the equations above. We know that the entropy change, and because this is irreversible, this is a real process, it's the greater than sign that applies, right? So the entropy change has to be greater than the integral from 1 to 2 of delta Q over T. Okay. Now, the reason I put it in this form is because I want you to think about the nature of the entropy change. Consider this, that the entropy change has to be greater than this integral of delta Q over T. What one might say is that the entropy change is going to equal the integral of delta Q over T plus some additional amount. So wouldn't that be just an alternative way of interpreting exactly the same equation? So we can rewrite this as, instead of saying that this entropy change is simply greater than delta Q over T, we want to know how much greater than delta Q over T it is. So we say that it's equal to the integral of delta Q over T plus some additional amount. And that additional amount we call the entropy generation. So again, it's just a different interpretation. Instead of noting that the entropy change is greater than a certain value, we want to know by how much it's greater than that certain value. That is, how much greater than the delta Q over T is it? And that amount is what we call the entropy generation. So the entropy change equals the integral delta Q over T plus some additional amount that we call entropy generation. Or just simply S gen. So I wrote out the word generation above, but often we'll just abbreviate it as S gen to represent the entropy generation. Okay. Now, let me rewrite that. It's kind of sloppy down here. All right, so I'm just going to rewrite it. So the entropy change equals the integral delta Q over T plus some additional amount. And then let's just note here the signs associated with that. Okay. Now, first of all, let me just back off for just a second. What if we weren't talking about an irreversible process? What if we were just talking about a reversible process? Well, if it were a reversible process, then the entropy change would equal the integral delta Q over T, right? And there would be no entropy generation, right? But for a irreversible process, a real process, there is a certain amount of entropy generation, and that's what we're trying to figure out. I'll note that the entropy generation will be greater than 0 if it's a real process, right? In other words, for an irreversible process. And the entropy generation will have to equal 0 for an internally reversible process. It can never be less than 0, right? So the entropy generation can never be less than 0, right? It either has to be equal or greater than 0. Okay. Now let's do this. Let us look at what's called an isolated system. Now, I did mention isolated systems like that very first week of class as we were talking about different types of systems, different limitations. You may recall that an isolated system is one that has no interaction with the surroundings. Included in that would be no heat transfer. So let's say we had a perfectly well insulated container. That would be an example of an isolated system. Our entire Earth and the atmosphere above it might be another example of an isolated system, one that's just sitting there and is not interacting with its surroundings in any way. I mean, the Earth, after all, is just floating in the pure vacuum of outer space. So there's no way that we can interact with anything around us, right? Certainly there's not going to be any heat transfer. If there's no substance to hold that heat, how can you transfer heat to it? So let's just look at a certain isolated system, and I'll note that for an isolated system, the heat transfer is going to have to equal 0. So what does that tell you from the equation above for the entropy change? By the way, I had really intended to label this equation C, the equation up there for entropy change. So if you could just add that to the notes right up here as well. All right, so we're looking at an isolated system now. And what would be the entropy change? Well, I mean, we know from C Yep, so from C, we know that the entropy change is the integral delta Q over T plus a certain amount of entropy generation. But if it's isolated, there is no heat transfer, right? If Q is 0, we could have also just simply said delta Q is 0. I mean, there's just no heat transfer, right? So this term goes away, and we find, therefore, that the entropy change equals the entropy generation as long as we have an isolated system. And of course, we would note that this entropy change, well, it has to be either greater than 0 or equal to 0, right? Right. So for an isolated system, we would simply note that the entropy change is the same as the entropy generation, and that has to be a number, you know, that's either greater than 0 or equal to 0, right? Okay. Yep, thank you. All right, so now that we understand that, now we have to take it even one step further. What might be an example of an isolated system? Well, what if we were to take a system and its surroundings and call those an isolated system? And again, this gets back to the whole planet Earth, right? Any system that we analyze is here on the surface of the Earth. Any heat transfer is going to go to the surroundings, and nothing is going to go to, well, what's beyond the edge of the atmosphere of our Earth. So let's consider a special type of an isolated system. Let's consider that a system being analyzed and the surroundings combined are an isolated system. Okay. And again, in the context of systems that are operating here on Earth, that's really not a bad assumption to make. Okay, so if we do indeed assume that the system plus its surroundings are this isolated system, then let's go ahead and rewrite the equation above. Okay, so I'm basically taking this equation here, and I'm going to rewrite it. And we'll note here that we're going to now use a slightly different notation. I'm going to say, instead of just S2 minus S1, why don't we call this S2 minus S1 total, because this includes the system under analysis as well as the surroundings. So the entropy change total equals delta S for the isolated system. We know that this equals the entropy generation. But what we also know is that there's two processes essentially taking place. One is the process involved with the system that we're analyzing, and the other is the process involved with the heat transfer between the system and its surroundings. So we've got both the system and the surroundings, which are part of this isolated system. So I'm just going to say that this is then equal to simply delta S for my system that's being analyzed plus delta S for the surroundings. And then this has to be greater than or equal to 0. Okay. So I've taken my basic equation for the entropy change for a real and irreversible system. I've then simply modified it by saying, let's look at a special case, which we call the isolated system. Then we said, well, this isolated system really contains some system under analysis plus the surroundings. That's our isolated system. And that isolated system, again, which represents the sum of the entropy change of the system and the surroundings, that's got to equal something greater than or equal to 0. Okay. Now, this is really the increase in entropy principle. Okay. The previous statement wasn't technically the increase in entropy principle. That simply told us that the entropy change had to equal some integral delta Q over T plus some additional amount called entropy generation. Now what we're doing is we're saying, well, this entropy generation for this isolated type of system has to be greater than or equal to 0. Okay? And again, we can look at it this way, that the greater than is implying the irreversible, the equal to implies the reversible system. Okay? So this is really the increase in entropy principle. Yes. Okay. This shows us pretty clearly that there will be an entropy change, that entropy change we call the entropy generation, and that it's going to be the sum of the entropy change of the system plus whatever is surrounding it. And again, combine the system and surroundings, all are isolated from the rest of the universe. So just a couple of final notes, just to summarize all this, put it all together. What if I were interested in trying to quantify delta S for the system, which I'll just abbreviate SYS for system? How might I actually find that? Well, remember, entropy is a property, right? As long as I'm analyzing a process, I should know what my initial and final state is. Or for that matter, even if I have something like a steady flow process, I should know what the entropy in is and the entropy out is. So we can find the entropy change for the system just by using our property tables. Or perhaps if we have an ideal gas, then we'll have to use some sort of a ideal gas equation of state. But still, this is just going to be found as S2 minus S1. And these are just properties. So this is just going to come from our tables or possibly an equation of state. Okay. Now what about the surroundings? So again, I'm just going to abbreviate this SURR so I don't have to write out surroundings over and over again. How might we go about calculating this? Now, we know that the entropy change, by its definition, is just the integral of delta Q over T, correct? As long as the delta Q over T is taken for an internally reversible process. Okay. Now, what do we also know about the nature of the surroundings? And again, remember, we're talking about the surroundings as if it's essentially the entire planet, right? The entire planet, all its atmosphere. Is there going to be any heat transfer made by any one particular process that would cause the temperature to change? I mean, even if we had a huge, maybe 1,500 megawatt electric power plant producing massive amounts of heat, it's still teeny tiny in comparison to the overall planet that we live on, right? So there's really nothing that I can do, at least as far as any one individual process, that is going to do anything to cause the temperature of the planet to change, right? I mean, the planet is too huge. So we can approximate this then as, well, if the temperature is not going to change, it's just going to come out of the integral. We have the integral of delta Q. I should really show this as a process for the surroundings. So let me just put a 1 to 2 and a 1 to 2. And then we would note lastly that the integral of delta Q is just Q, but this is the heat transferred to the surroundings. So this is then just going to equal Q surroundings over the temperature. And let's just assume that the surroundings have a temperature of T surroundings. So it turns out that delta S for the surroundings can be, very accurately approximated by simply Q surroundings over T surroundings. Now, shouldn't this really say Q12? Kind of, but not entirely. Keep in mind that Q12 would actually represent the heat transfer to the system based on our sign convention. But the heat transfer to the surroundings is actually equal but opposite to the heat transfer to the system, correct? So we could also note simply that Q surroundings is just the negative of Q12. Keep in mind that everything we talked about before with regards to absolute value still applies here. All of our heat terms, all of our work terms are just magnitudes, okay? So from here on out, they're just magnitudes. So this would represent the negative of the heat transfer to the system. If the heat transfer to the system is positive, then the heat to the surroundings must be negative, right? It's also possible to have heat being removed from the system, in which case the heat transfer to the surroundings might be positive if Q12 is negative. But nonetheless, this is the equation that we're going to deal with. To find the total entropy change then, again, we're going to do nothing more than add together the entropy change of the system and surroundings. So therefore, just to kind of finalize all this, the total change in entropy, which we could just as easily write as delta S total, which we could also just as easily write as the entropy generation. This is going to equal the sum of the entropy change of the system. So we'll just write it as S2 minus S1 for the system, plus the entropy change associated with the surroundings, which is Q surroundings over T surroundings. And this has to be greater than or equal to 0, right? Okay, so this is really the form of the increase in entropy principle that we are going to use on a daily basis. Okay. Okay. So essentially, any process that takes place must be accompanied by a change in entropy. And I would note that that entropy change is going to have to be positive. Right? Now, one last thing to note here. It is certainly possible for either the entropy change of the system or the entropy change of the surroundings to be negative. But combined, when we're looking at this isolated system that we call our system being analyzed plus the surroundings, that is, plus our environment, when we look at that as the isolated system, it's that sum of the entropy change that has to be greater than or equal to 0. You could still have a negative entropy change associated with either system or surroundings, but as long as the total is greater than 0, then we know that the process is possible. So this is how we're going to be able to analyze processes. So are there any further questions on this? Okay, a couple of other final things to note, and then I want to go on to some example problems. First of all, we know that we don't have total entropy data in our property tables, right? We have, well, specific entropy data, right? Everything on a per unit mass basis. So let's just remember that a total entropy change is just going to equal the mass times the specific entropy change. Okay, so it's really the specific entropy that we're going to get out of our tables, and it's the mass that through some sort of calculation we're going to have to figure out in our particular problems, right? So this can very easily get plugged in above, and this applies to the system. So you can just note that that really should get plugged in up above there. The same thing would apply to the heat transfer term, right? We would note that the total heat transfer, and here I'm talking about the surrounding specifically, is not something we typically know. Sometimes we do, sometimes we don't, but we know that this is just going to be the mass times the heat transfer per unit mass to the surroundings. Just keep that in mind. Now, quite frankly, we typically don't see this m times lowercase q. Most of the time, we just have some fixed quantity that's being transferred to the surroundings. So even though this is true, maybe I'll just put an x through it right away and just say it's not usually used. Okay. In other words, q surroundings, which again equals the negative of the heat transfer from the system, is essentially is always going to be known somehow. Okay, we'll either have to calculate it or it'll be given to us, but it's something that would be known. All right, another thing that I want to note is that the equation for the entropy change above will also apply both to open systems as well as closed systems. Okay, so certainly the equations that I've been deriving here have been for closed systems where we have some fixed mass of material that's being analyzed, but it doesn't have to be. Okay, so I'll note that the above applies to closed systems where 1 represents the initial and 2 represents the final state. Right? I mean, this is something that we should already understand. But it also applies to open systems. Now, most of the time when we look at open systems, we're going to look at single stream steady flow problems. So, for example, for a single stream steady flow process, we would note that instead of showing just delta S total, we'll put a dot over this. So the rate change in the total entropy, or the rate of entropy generation, this is going to equal not the entropy change, but the rate entropy change. So in other words, the mass flow rate times the change in specific entropy associated with the system. Okay. And then plus the rate of heat transfer to the surroundings over the temperature of the surroundings. Okay? So even though I haven't specifically derived this increase in entropy principle for the open system, or for that matter for a steady flow process, or even the single stream steady flow process, I will just note that it will still apply. I mean, I could go through and take a lot of time to derive it, but again, it's just really not worth it at this point. Let's just recognize that this equation up here at the top and this equation down here at the bottom are essentially the same equation. One is written as a rate, right? This latter one is written as a rate equation, and the former one is just written as a total equation. Of course, I need to end this all with a must be greater than or equal to 0. Okay, so this is just another version of the increase in entropy principle. It's this lower version that's typically going to be used for the open systems, and it's this upper version up here that's typically used for the closed systems. Let me again remind you, before I do examples, that entropy is a property. You're going to use it just like any other property. If you have a two-phase mixture, then the entropy is going to be SF plus the quality times SFG. If it's a compressed liquid and we don't have good compressed liquid tables, then the entropy of a compressed liquid is going to be about the same as that of a saturated liquid at the same temperature, right? If we have superheated vapor of some sort, then we go into the superheat tables, we go into the subtable at the appropriate pressure and then at the appropriate temperature, and we'd be able to find the entropy of superheated vapor. I mean, again, entropy is just a property. So from the standpoint of finding the entropy change of our system, whether it's an open or closed system, we just use our tables, okay? Or again, if it's an ideal gas, we might want to use one of the ideal gas equations of state. But that's how we're going to solve problems using this increase in entropy principle. Now, what do these problems really look like? Well, let's look at one. So the first one will be 7-48. So I've got that here open up on the computer already. So let's give us a second, and our producer will flip it over. This is problem 7-42 from the current edition, the 8th edition of your book. Not sure what that's all about. Well, in the meantime, if anybody has their own book, fine. If not, yeah, I mean, I'd still like the computer to come up if it can, but here's the problem statement. Just, oh, there it is. It's up now. Okay. All right, so let's look at this particular problem. This tells me that we have a rigid tank. It says a 0.5 cubic meter rigid tank contains R134A, initially at 200 kilopascal and 40% quality. It says heat is now transferred to the refrigerant from a source at 35 degrees Celsius until the pressure rises to 400 degrees Kelvin. I'm sorry, 400 kilopascals. And then they want us to find the entropy change of the refrigerant, the entropy change of the heat source, which is the surroundings, right? And the total entropy change for this process. Now, if you read this problem, you first might notice that it sure appears to be a first law problem, doesn't it? This looks like just like the problems we saw back in chapter 4, right? We're given a rigid vessel of a certain volume. We know the initial conditions. We know one property at the final state. We know that because it's a sealed rigid vessel that the volume and the mass are the same, so the specific volume is the same. We know, therefore, that we have the final state, right? We know the temperature it's given, the pressure is given, and we know that the final volume and the initial specific volume have to be the same. So this sure sounds like a first law problem, doesn't it? However, if this problem were out of chapter 4, instead of asking for the entropy change, it would have asked us to determine the amount of heat transfer for this process. Here, it doesn't ask me for the amount of heat transfer, yet we know we need it, right? I mean, how else do you find the entropy change of the surroundings, the heat source, unless you know Q? I mean, after all, Q over T is the entropy change for the surroundings. So it turns out that these problems here out of chapter 7 are just like the chapter 4 problems. They just take us one step further. Instead of finishing with how much heat transfer takes place or how much work is there, it goes one step further and it says, does this problem work? I mean, they don't use those words, but that's really what they want to know. Do we satisfy or do we violate the second law of thermodynamics? Is the entropy change greater than 0, or is it equal to 0, meaning that it's an ideal process, or is it less than 0, meaning that it's impossible? I mean, that's really what this author is asking us. I don't know why he bothered with parts A, B, and C. Does the process satisfy the second law? Period. You solve exactly the same problem as the one that we're about to do. So let's do it then. All right, so it's a sealed rigid tank. Again, it's problem 742 from the 8th edition. All right, so let's just draw it out. Here's our tank. We're given the volume is 0.5 cubic meters. And it's a tank, right? It's sealed, it's rigid, so we know V1 and V2 are the same. We don't know how much mass is in it, but again, it's sealed, it's rigid, so we know that the mass is constant, and therefore we know that the specific volumes have to be the same. We know that it's refrigerant 134A that's inside this particular tank, and we're given an initial pressure and quality. So the quality is 40% and the pressure is 200 kilopascal. And we're also given the final pressure, P2 of 400 kilopascal. They do tell us that heat is transferred from a source, and that source is our surroundings, right? So the temperature of the surroundings is 35 degrees Celsius. And they want us to simply determine the entropy change of the refrigerant, so delta S for the system. They want us to find delta S for the heat source, which is the surrounding medium, so delta S for the surrounding, and the total, right? So what is delta S total? In other words, what is the entropy generation for this process? All right, so this is what we're trying to find now. Well, if you think about it, once again, it's just a first law problem. We're just adding a little bit onto the first law problem to turn it into a second law problem. But it's still a first law problem. 99% of the work is the first law problem. And it's only at the end do you have to then look up some entropy data and find Q for the surroundings to determine whether the second law has been satisfied or not. Well, with this in mind, how do we solve the problem? Well, first of all, we know that delta S for the system is the mass times the entropy change for the system. Do we have a way of finding the entropy? Yeah, of course we do, right? We know initial pressure and quality, so the initial state is set, and we know the specific volume at 1 is the same as V2, so we know V2 and P2, so we have two properties at the final state, so the final state is set. So we know all our properties, so yeah, S1 and S2 are known. What about the mass? Well, we've done this quite a few times. We know mass is just volume over specific volume. We're given the initial volume. We can use the initial properties to find the initial specific volume, so we can very easily find the mass. So yeah, we can find the mass of the system right away. What about the mass of the, what about the entropy change for the surroundings? Well, remember, that's just Q over T, and for the surroundings, it's the heat transfer to the surroundings divided by the temperature. Now, we know the temperature of the surroundings. How do we find the heat transfer to the surroundings? Well, we know that the heat transfer to the surroundings comes from the system. They're just equal but opposite. So that's just minus Q12. And of course, the only way we have to find Q is the first law. So the first law tells us that heat transfer minus the work, although I guess we put the work over onto the right-hand side for most of these problems, didn't we? Negative on the left or positive on the right, it doesn't really matter. I guess I'll be consistent. So this equals the mass times change in internal energy plus the kinetic and potential energy changes, and then plus the work. Okay. Now, it turns out that there is no work, right? There's no change in volume. It's a closed system. There's no mixers. There's no shaft work. There's no springs. There's no electric resistance. I mean, there's no work, right? So that's clearly zero. We also are going to assume, like we did for all these problems, that there's no kinetic or potential energy changes. Even if there was, we don't have enough information to calculate them, so we have no choice but to assume they're zero. So it turns out the only way to find the heat transfer is just to know the mass and the change in internal energy, which we know, right? We know the initial and final state. We already know how to calculate the mass. So we know the heat transfer. We can therefore find the delta S for the surroundings. And then we add the system and the surroundings entropy changes together, and that gives me the total. So it turns out it is just a first law problem with a little second law thrown on at the end, just to make us happy Well, we're always happy as engineers knowing that the systems we're designing can actually work in the real world, right? Okay, so the second law is an important thing. It might just sound like a little bit of thermodynamic hocus pocus, but it really isn't. It's necessary. If the system doesn't satisfy the second law, it won't work. So let's solve the problem. All right, we've talked about the methodology. Now it's just a matter of getting the numbers. So we'll start at P1 and X1. We know that it's the refrigerant 134A. We know that it's pressure, so that means we go into table A12. And we can look up the values. We need three things, right? We need volume, internal energy, and entropy. So V1 is VF plus the quality at 1 times VFG. U1 is UF plus quality UFG. And S1 equals SF plus equality times SFG. Now, in the interest of saving time, we've seen problems just like this before. I don't think we need to go through all the mathematics again. We know how to look up the data. We know how to plug it in. The only thing different, perhaps, is that for this problem, we have entropy data that we need as well. But the entropy data is just like all the rest of the data on our tables, right? There's no real difference there. But let's just go to that table once just to make sure we can see that. Okay, so here's our table A12, here's our refrigerant pressure table, and there's the data, right? We have UF, UFG, UG, HF, HFG, HG, SF, SFG, SG. Everything is there that we need. So we just come down to the 200 kilopascal line, we read across, and we find our SF and our SFG. Again, we've done this so many times before, I'm not going to do it again. I'll just give you the numbers. So we go through a little bit of mathematics, and we get that 0.0404 is the specific volume. The specific internal energy is 112.76 kilojoules per kilogram. And with regards to the entropy, we get 0.4678. And the units are kilojoules per kilogram per degree Kelvin. Okay, so again, I'll let you go through the math yourselves at home. Hopefully you'll get exactly the same results that I found. All right, let's find the information at state point 2 now. So at P2 and at V2 equal V1, well, as it turns out, we're still going to be in the two-phase region. We don't know that yet, but we do like we always do. We're going to go to table A12, and we'll find that V2 is actually between VF and VG for this particular substance at this particular pressure. Keep in mind the pressure at 2 is higher than it was at 1, but still you'll find that VF and VG bound V2. You can go to the 400 kilopascal line and read over, and you'll see that V, as I found it, was 0.0404. VG is 0.0456. So I'm clearly less than VG, and I'm clearly above VF. So it has to be a two-phase mixture. So therefore, it's a two-phase mixture. And because it's a two-phase mixture, we're going to have to use our given specific volume data in order to find the quality. And then we're going to have to use that quality to find, well, again, the internal energy and the entropy. So V2, which equals V1, equals VF plus the quality at 2 times VFG. And again, I'm not going to go through the mathematics, but if you do so, you get that the quality at 2 is 0.7857. I'm sorry, that's right, 0.7857. Okay, again, you can do this on your own at home and verify that I've done the numbers properly. And then, just like we did before, U2 is UF plus equality at 2 UFG, and S2 is SF plus equality at 2 times SFG. If we just plug in the quality from above, we end up with the internal energy of 198.34 kilojoules per kilogram, and the specific entropy of 0.7813 kilojoules per kilogram per Kelvin. So now we have all the data. Next, let's find the mass, although we could have found the mass earlier. Well, we know the total volume is given as a half a cubic meter. We divide it by 0.0404, and this gives me 12.38 kilograms. So we have the mass. Now let's solve the first law. Okay, so heat transfer equals change in internal energy. So once again, I'm letting you plug everything in on your own. We know the mass, we know U2 and we know U1. We just plug in all the numbers and we get the heat transfer of 1,059 kilojoules. And I'll put a little plus sign on this just to remind us that heat is being added to the system, which would mean then that heat is being rejected from the surroundings. So Q surroundings is then just the negative of the above, so minus 1,059 kilojoules. Okay? And now we're practically done, right? We have everything we need. Let's find delta S for the system. Again, that's just the mass times S2 minus S1. Again, plug in all the numbers yourself, and we end up with 3.880 kilojoules per Kelvin. Note that the specific entropy units would be kilojoules per kilogram per Kelvin. Then the mass has kilograms, so that the mass units cancel. So we get total entropy units of kilojoules per Kelvin. So there's the delta S for the system. Now, does that mean that this process is possible? It's a positive number after all. Not entirely, right? We know that the total entropy change has to be positive for this process to be possible, that is, for it to not violate the second law. And we haven't done that yet. We have to first find delta S for the surroundings, and then add the two together and see what the total entropy change is. Well, so Q surroundings over T surroundings. So we have minus 1,059 kilojoules over, and then keep in mind that like all problems of this type, we're not going to use Celsius. That's just an arbitrary temperature scale. We'll use the absolute scale in Kelvin. So don't forget to add U273.15 to get this into Kelvin. And we go through the mathematics here, and we get minus 3.439. And the units are the same, kilojoules per Kelvin. Now, this is a negative number, so you might look at that and say, oh, well, it's negative. I guess the process can't happen. But no, you have to look at the total entropy change. We're not there yet. So now we'll get there. So delta S total, which is what we call our entropy generation, is just the sum of the above. So we add the two together, and we end up with a positive 0.442 kilojoules per Kelvin. And the fact that it's a positive number tells me that this process is possible. Okay? So there is a total increase in entropy, thus the name increase in entropy principle. The increase in entropy is positive. It's possible, right? So we can say that this is an irreversible process. We can say that it's a real process. We can say that it's a possible process. We can say that it satisfies the second law. There's all sorts of ways that we can phrase this at the end. But the bottom line is, theoretically, one could build this particular machine, and it would work. Questions? All right. If you're beginning to think, well, maybe these entropy problems aren't that difficult, well, that's exactly what you should think. I've never thought of entropy problems as difficult. They're just different. They're just first law problems with that little twist at the end. Let's look at a steady flow process now to show how we would do these types of problems for these open systems. And this will be problem 154, also from the 8th edition of the book. So let me put that up here. So this is on the board. Let me go ahead and read it. I don't think we'll have enough time to finish it today, but at least we can talk about it and make sure we know that it's a doable problem. We're told that steam expands in a turbine steadily. And again, I don't know why the author always uses the word steadily. These are all steady flow problems. So steam expands in a turbine steadily at a rate of 40,000 kilograms per hour, entering at 8 megapascal 500 C, leaving at 40 kilopascal as a saturated vapor. Wow, this is even nicer than many of the first law problems. Here we're given both the inlet and the exit conditions and the mass flow rate. Wow, that's great. Not much left to do. It says if the power generated by the turbine is 8.2 megawatts, so that's the rate of work output, then determine the rate of entropy generation for this process. It says assume that the surrounding medium is at 25 degrees Celsius. So again, this sure sounds like a first law problem. It is a first law problem, except we just have to take it that one step further at the end. We still have to find the rate of heat transfer. We have to find Q dot using the first law. But once we have Q dot, we'll note that that heat transfer rate is equal but opposite to the heat transfer into the surroundings. That will allow us to find the entropy change of the surroundings. And of course, we're given both the inlet and exit states for what's passing through, that is for the steam going through this turbine. So we can easily look up the entropy at the at the inlet and exit states. So we can solve the problem. Let me just illustrate it. So here I have a steam turbine. I'm just going to use 1s and 2s to represent the inlet and the exit state. We are given a mass flow rate of 40,000, and that's in kilograms per hour. We'll have to convert that to seconds eventually. We're given inlet pressure of 8 megapascal and an inlet temperature of 500 C, and we're given an exit pressure of 40 kilopascal, and that it's a sat vapor. All right. We're told that the turbine produces 8.2 megawatts, so that's the power output, and it's work output, so it's positive, right? And then we're also told that the surroundings are at 25 degrees C, and we're trying to find the rate of entropy generation. So S dot generation, which by the way is just the rate change in the entropy, is what we're trying to find. And it's the total entropy generation, so we really should write the word total here, just to remind us that we're talking about the total, not just the entropy change of the system, not just that of the surroundings, but for the total. Okay. Now, again, as I was reading through the problem, hopefully I described how it was solvable. We know that the rate of entropy generation is just going to be the rate change in the entropy of the system plus the rate change in the entropy of the surroundings. So it's going to be m dot times S2 minus S1 for the system plus Q dot over T for the surroundings. So this is what we're trying to solve for. Now, again, we have the initial state, right? Two properties. We know the initial state. We know the final state. It's, we've got a given pressure as well as that it's a saturated vapor. So we could very easily find S1 and S2. We can find m dot. It's given to us. All I have to do is change units. I know T surroundings. The only thing I don't have is the rate of heat transfer. But I mean, that's what the first law is all about. First law for a single stream steady flow process, we know that the heat transfer minus the work, or really the power, so rate of heat transfer minus rate of work, is the mass flow rate times the enthalpy change plus the kinetic energy change plus the potential energy change, although we'll note that like so many of the problems of this type, we have no information at all about the geometry, so we can't find the height change even if we wanted to. We know nothing about the area or the diameter of the inlet or exit. If they had given that to us, knowing the mass flow rate, I could certainly have found the velocity, right? I know that mass flow rate is velocity times area over specific volume. I could easily find the velocity, but I don't have that information. I don't know how big the pipe is at the entrance or the exit. So again, I'm just going to have to assume that there's no change in kinetic energy. So ultimately, to find the heat transfer rate, I can just use this version of the first law. I know the mass flow rate, I know the power, I know the initial and final state, so I can find H1 and H2. The only unknown is the heat transfer rate. So the problem is done, right? You solve the first law for Q dot, you change the sign because the heat to the surroundings is the opposite of that to the system, and you plug it into the entropy generation equation above, and the problem is done. So I will complete this problem for you. You will find, for those of you that want to figure this out at home, the total rate of entropy generation will be 11.4 kilojoules per second per Kelvin. So if you want to aim for that for your final answer, you're welcome to do so. But I will complete this problem next time, but I'm all out of time. So until Wednesday, see you then. Remember, you have homework due on Wednesday. Don't forget to bring that with you. And also, there's a few homework sets from last week that weren't picked up yet, so please don't forget to pick that up. With that, we're done for the day. Any last-minute questions? Great. Thank you. See you on Wednesday.